So far, we've been talking about the resting membrane potential, and you should now have some intuition about why it's there and how to calculate its magnitude from ion concentrations and permeabilities. If you're still a bit fuzzy about why there's a voltage across the membrane at rest, you may want to go back and review the previous section. Everything we've been talking about so far is in terms of steady states. Basically, what happens if you let the system run, in principle, forever, until everything settles into a state where there's no net change. Now, the function of the nervous system is all about sending signals. Signals from senses, signals telling our muscles to move. By now, you've probably also guessed that we'll be sending those signals in neurons by transiently changing the membrane potential. The existence of a resting potential primes the system for action, but a signaling mechanism wouldn't be terribly useful if it never changed. We'll talk about the active mechanisms that allow us to change the membrane potential and how these give rise to neuronal signaling in the next section. But before we get there, we need to address some of the passive properties of the membrane that govern how fast the membrane potential is able to change. We've already introduced the parts that we'll be talking about: the membrane, the intracellular and extracellular fluid, ions, and channels. But now we'll go beyond how they behave at steady state and look at how they behave across time.